Charles. I'm a PhD student at La Trobe University, and I'm absolutely stoked to be here. It's my first time at USR. This is my first package that I'm working on and my first paper. It's a lot of firsts. And I'm here to talk about meta-analysis of medians, the first project in my PhD. So in a nutshell, what am I going to talk about? Meta-analysis is a statistical method of evidence synthesis of many studies, bringing together lots of studies. And conventional tools within meta-analysis require an effect and a variance of the effect. And why do the tools require this? Because of something called inverse variance weighting, as in we're weighting them by the inverse of the variance. We need the variance in order to weight the studies. Why might we want to weight studies? Well, they're not all created equal. And when we're combining lots of studies together into an analysis, some of them maybe are a little bit funky, some of them maybe had, in clinical trials, which, Casey, that was just a wonderful precursor for my talk. I was thinking, I didn't talk about control groups and treatments and whatnot, and you gave this wonderful RCT talk, so thank you. And so, for example, in R, a tool that's used frequently is, come on in, guys, and take a seat, you're fine. Thank you for coming. So in my experience, my limited experience as a student, metafor is the most commonly used meta-analysis package. And its first arguments that it asks for is the effect, yi, and the variance of that effect. But what if, in a particular study, no variance is actually reported? What if they report the median in an interquartile range? So in this talk, I'll give a woefully glib intro to meta-analysis, where I am still getting my head around the theory myself. I'll try to contextualize it a little bit and look at an illustrative meta-analysis data set. And also have a look at some exploratory data, Shiny apps, my very first Shiny apps that I built to explore how well our estimator worked, and discuss the current solutions, and finally talk a little bit about the package that I'm developing to solve this problem. So first of all, what is a meta-analysis? So as I said, it's a method of evidence synthesis. And I was putting this slide together last night, and I was chatting to Nick from the Numbats group, and I was discussing this as whether or not I should include the term evidence synthesis. But I think I should, because I just learnt it. I just came back from Stockholm, where I went to the evidence synthesis hackathon. And as a student who switched from mathematics, just like Casey, I come from a mathematics background, and I've switched in my PhD into statistics, so I'm catching up a bit. And I had focused on the meta-analysis component, the statistical analysis, but I have since learnt that meta-analysis is really just one step in a much larger protocol of evidence synthesis. How can we bring together lots of studies? So, say, for example, we're interested in some clinicians may be interested in, Casey came wonderful, that was just perfect, thank you. So as Casey was describing in the randomized control trials, we may be interested in comparing a control group and a treatment group. And what if some clinicians come together and they say, we're interested in whether or not this particular drug works, and well, let's have a look and see what evidence there is out there. And say 7 studies have been done over time, and how can we combine the results of all these studies to come up with a more robust conclusion about the efficacy of this treatment? And because you're combining multiple studies, and because there's all sorts of reasons that it might be impractical to get your mittens on that raw data. You may only have the summary statistics reported in the study to work with, especially when they're combining together many, many studies, 20 studies, 50 studies, and a meta-analysis. It can just get impractical for historical reasons, for data warehousing reasons, because researchers do lose their data sets over time. There's all sorts of reasons it can be impractical. So meta-analysis is the practice of what if we don't have access to all that raw data? What if we only have basic summary statistics? Yes, and the next slide is the example that I was hoping was there. So here's an example data set from a meta-analysis. This is, do not ask me too deeply about these medical terms. D-dimer levels in preeclampsia was what it was looking at. It was a meta-analysis looking at hormone levels in maternal health or something like that, and that is the depth of my knowledge about D-dimer levels in preeclampsia. But they considered 7 studies. So we've got down here the 7 studies, and they were published in different years. We have, and that's why Casey's talk was just wonderful, because here I couldn't quite fit in the headings for the columns, so I had to sort of shorten them to get all the data onto the slide. But I wanted to show that this is the structure of the data that meta-analysts are frequently dealing with. So they'll have some study, and then each row represents the results of that study. And this is all they've got to work with. So they've got the mean of a control group, and they've got the variance for that control group and the sample size. And they may have the treatment mean, standard deviation or variance of your treatment group, and the sample size for that. And that's all they're working with, is these means and standard deviations and sample sizes. So how can we combine that information and draw and infer from there? And that is the study of meta-analysis. So so I'll come and lost my place and coming back. Right, so of course looking at this, they want to say, well, combining these studies, does the treatment work? And so they construct the model by saying, well, we're interested in whether or not this medical treatment works. And so in the most basic sense, a meta-analysis may look at the effect of the study, and assuming that there's some true effect out there and sampling error. So this is just a straight up, coefficient linear regression model. There's absolutely nothing going on, no moderators or anything like that. And there we've got the maths of our fixed effects model. Now, the rub is that we weight the studies by inverse variance. And so in order to weight the studies within the model, we need the variance. But so this is the problem that I'm trying to solve. So, what if they have reported asymmetric measures? This poses a challenge in meta-analysis. And of course, not all studies are created equal. So weighting is one way to account for strength or weakness of a study, but there are also differences created by, say, for example, let's look at the drug treatment example. What if everybody they looked at was under 25 because the study was performed at a university and everybody that they sampled from was students? So maybe young people are going to respond to this drug in a different way. So each study has their own little confounding factors. So in that case, we may want to build in a random effect to account for the variation between the studies. And so in this case, we assume that there's a true effect, but there's also unique factors that are contributing to the effect for this particular study, as well, of course, as the sampling error. And we can also add moderators and so forth, just as we do with linear models. So returning back to our example, we have our 7 studies, and we have means and standard deviations for the first 2. So those are fine. The metafor package would be very happy with those. But where we run into issues is where we have the median and the range reported, or the median and the interquartile range. So this is what they did. And this is conventionally what people do, is they'll just leave the studies with the medians out. I don't know how to pass it into the software, such as Metafor or RevTools is the one that comes from Cochrane. And they both require this effect and the variance of the effect. So here I've just filtered this example data set by the means to produce a forest plot meta-analysis. And this is so here the squares are sized by that weight of the weight that we're assigning to that particular study, the strength of the study. So this one has been weighted very small, and you can see that it's got much larger variation. These represent the confidence intervals, which are given here, as well as an estimate of the effect. And here's the name of the study. So there were only 3 studies that reported the mean. Here in 91, 97, and down here 2003. So those are the 3 studies that they performed their meta-analysis on and published their beautiful forest plot with 3 studies in it. Another method, there's several papers, and they're still rolling out at the moment actually, that have been developed and they're kind of building on top of each other. And their approach is to approximate the mean and the standard deviation from the reported quantiles that we have to work with. And then you have some approximation of your variance for your effect. It can work quite well at times, but the no free lunch theorem kicks in, and no algorithm works for everything. And I think there's something to be said for considering whether or not we're forcing asymmetric data into symmetric conditions. So we wanted to look at can we continue to work with medians? So there's a well-known result that I absolutely did not come up with that has been around for a while that says that we can estimate an we can approximate the variance of the sample median thus. So by this formula where we consider the density evaluated the median squared, and then we've got 4 times the sample value. So the really interesting part is here in the equation that we're evaluating the density at the median squared. But we don't know the median, and if we only have these quantiles to work with, if I've only got a median, an interquartile range, and a sample size, I don't know what the density is, and I don't know what the true median is. But it turns out that the log normal and the normal distributions both do a really nice job, particularly the normal distribution. If you assume instead that, we don't know what f is, we don't know what the density is, but let's just assume naively that this is a normal density. And then using the quantiles that we have our hands on, interquartile range and the median, we can approximate the parameters. We only have 2 parameters, and so we've got 2 equations, and we can approximate our parameters using a little bit of algebra to shuffle things around. And then we have an approximation of the density. So we choose the density naively, estimate its parameters, and evaluate it at the sample median. And it turns out this does a really nice job of approximating the density. So which choice of G? This is where I started in my project. And to switch to A. So I built so my supervisor said to me, why don't you, experiment with it and see what, how well does it perform for various different choices of G. And so I was interested in, I've loaded up the same Shiny app twice, haven't I? All right. What's the line? Shiny V. That's the one. I just launched my... Yeah, right, cool. Okay, so here's my distribution, and I'm interested in choosing a G to approximate it by. So in this case, I've got, it's defaulted to a log normal distribution. Its true median is 2.72 apparently. And I built this little Shiny app for me to learn about how densities work and whatnot. So here I've plotted the density so I could see what its shape looks like because I'm just learning statistics at the moment. And I've, here in the green line is the true median. And the blue line is the log normal distribution with the parameters estimated. So at the moment they're over each other because I'm using the same density. But if I choose a different one, so whoops, that was the wrong one. That was the one that said I've just loaded up an older Shiny app and I haven't installed all the packages that go with it. But if I flick over to a Weibull distribution, here I'm approximating using the log normal density evaluated at the sample median. But here is where we're really interested, and it does a really nice job. Just at this point, like sure it deviates, but at the true median, the densities are doing a really nice job of approximating it. And here I learned all about conditional panels for my parameters, and I was super proud of myself. But it turns out, it's a fun little toy to play with, but you can see as I'm changing different distributions, the log normal's doing a lovely job. I could also choose, oh no, I haven't. Sorry, this was a slightly older version of this app. I ran a workshop this morning, and that was well organized. The talk's a little cobbled together. So, but as I'm changing densities, it's still doing a lovely job of approximating the log normal, and you'll take my word for it, the normal also does a very nice job of approximating the density evaluated at the median. So that was my first little thing. So hopefully that's been reasonably convincing that this is a nice little technique for approximating the variance of the sample median. So my next step was to build a Shiny app considering various different simulations. So in this case, I was interested in, and this was me learning how to write simulations, which I'm very much still learning about. So here I was interested in running several different trials and being able to play with how many trials. Every time I change the number of trials, my Shiny app runs again. And I can choose different sample sizes, different distributions, and it gives me the results of the simulation. So here it's telling me what the true median is. And then what I'm doing is using my estimator to get the variance from which I can calculate a confidence interval and ask, does it contain the true parameter? And And then I ask, what proportion of the trials did I run? And this gives me my coverage. So how many of them contain the true value? How well is my estimator working? And here it's working really nicely. Like we wanted to see it hit around a 95% because we're using a 95% confidence interval. And regardless of the distribution I choose, it does a lovely, you see the log normal, because I'm using the log normal to estimate it, I get, almost exactly 95%. But as I choose different distributions, the coverage probability is still absolutely lovely. Whereas some simulations that have also run, that is in my next step to build in, I've got the simulations written in, but I just haven't built them into the package yet. When I tried it on some of the other estimators, it really produced a great deal of bias, interestingly, as the sample size reduced, which is not a great thing in a randomized controls trial context because of the fact that there's all sorts of practical reasons that people may be working with very small cohorts in medical research. And so the bias increases quite significantly, and that's because they're trying to force these medians into being means. Whereas we're not trying to do that. We're estimating an approximation of the variance of the sample median. I always get the estimation and approximation around the wrong way. And I even put it in my slides as a title to remind myself. Anyway, so this is the coverage probability. Here's the tabulated results from which I generated this coverage probability. And so here's my median, interquartile range, and the confidence interval produced using the estimator, and whether or not the median is inside that confidence interval. And then I started to play around with how could I understand this as a beginning, statistician in a way that would make sense to me. So I built a little visualization where I plotted the density so I could see its shape, and then I stacked the confidence intervals. So there's 1,002 trials, so I produced 1,002 confidence intervals, and I stacked them on top of each other so that I could get a kind of visual image of how well it was working. And here this dashed line is the true value. So if I turn off, if I show only the bad confidence intervals that don't contain the true value, you see none of them cross that blue dashed line. And I found this very illustrative for understanding how coverage probability simulations work. So I think that's all I want to say about this visualization. So now that we have an estimator, we can actually meta-analyze medians. And this is one of the challenges that I'm considering now in terms of implementing the package, and I'm very happy for people who come to me if they have ideas, in terms of how to take that data set that clinicians may be working with, which is in this tabulated format. How can I make it as easy for clinicians as possible? So I'm thinking a website where they can upload a data set that looks like this, and then it whirs away in the background and gives them the meta-analysis. So they will upload a data set about this size, and it whirs away for them. But seeing as this is a coding conference, I thought you might be interested in some of the actual code that was producing the analyses. So here skipping ahead to where we're up to meta-analyzing the medians. So here it gets a little bit tricky, and the reason why I've shifted into some P-mapping and whatnot is to deal with the fact that some of the studies reported ranges and some of the studies reported interquartile ranges. But toggling for that, we can calculate the variance or estimate the variance, the sample median, and meta-analyze those medians. Then we can also, by building in a moderator for whether or not the study reported a mean or a median, we can compare the results of means and medians within the meta-analysis and thus combine all the studies. So the current tools are quite specific, whereas ours is like everybody can come to the party, regardless of whether the range is reported as a number or whether it's given as two numbers, same thing with the interquartile range. So my next steps are to tidy up this package, get it out there, add in all the simulations I wrote to support. I haven't actually proved it mathematically. I'd love to. I don't know why the density does such a good job of approximating it. That's an open question for me. Finish up the paper, that's almost done, and make a nice, shiny dashboard for clinicians to access so they can meta-analyze their medians, and probably shift this into some kind of S3, which is going to be a learning curve for me. as an extension of the metafor package itself. So have a chat to Wolfgang, who developed the metafor package, and see how I can integrate it. And finally, the extensions from here is that there's a guy, Malcolm, over in the States, who's working on he was working on the tidy meta package of how to bring the tidy verse to the meta-analysis, and I was working on the meta-tidy package, I think. So we've joined forces, and the next step is to build the meta-meta package, how to tidy up meta-analyses. So we're both working on, say, Broom functions for meta-analyses and so forth. So yeah, and the next step mathematically is to ask, well, you know, if we can make inference about medians, can we make inference about the whole density itself from these quantiles? And what can we learn about distributions? Can I use something as flexible as the lambda distribution to infer things about the densities themselves rather than just a single quantile? So thanks for listening, and yeah, it was great.